So the next speaker is Časlav Brukner from Vienna University, and he will talk about quantum reference frames and covariance of physical laws. Please start.
Thank you very much. It's a great pleasure to be with you, even at the distance. I wish I could be in presence with you. It seems a very interesting workshop. And I would like to thank Tadashi Takeyanagi and his co-workers for organizing this workshop. It seems it's very impressive. It's not always easy to follow it from Europe because of a time difference. But your workshop is entitled Quantum Extreme Universe from Quantum Information. And I, myself, my background is in quantum information. And there are indeed a couple of ideas coming recently from this community that might be relevant for a broader field of researchers. And what I want today to tell you is something about efforts in Vienna to define and formalize the notion of quantum reference frames, and to show you that they may provide tools that might be interesting in considering, for example, low energy quantum gravity regime. And so this work has been done together with two students of mine, Anne-Catherine de la Hamete and Victoria Kabel, PhD students, and Esteban Castro, who is at the moment a postdoc at ETH Zurich, but moves soon for a permanent position to Paris. And so the title of the talk is Quantum Reference Frames and Covariance of Physical Laws. So let me just remind you on what we mean when we talk about covariance of physical laws. What we want to say is that there is a principle, and a very powerful principle in theoretical physics, that we believe that the laws of physics are of the same form, regardless of the choice of the reference frame. And so it doesn't matter whether I perform an experiment here in Vienna or maybe in Japan, or whether I do it today or tomorrow. So there are certain symmetries of physical laws and we believe that the fundamental laws should obey these symmetries. Now, if we think about the quantum mechanical system, and let's say a Schrödinger equation of a system from some reference frame, unprimed reference frame, let's think about this platform. I hope you see my cursor. And then we want to move this description from this reference frame to another one, which is a prime reference frame. Then we correspondingly with this transformation have to transform quantum states, but also the dynamics as given by the Hamiltonian. And in general, if this transformation between two reference frames is time dependent, we will have also in addition this time dependent change. And now the symmetry is something which we define as a specific transformation S, which leaves the functional dependence of the Hamiltonian as the, for example, function of position momentum invariant. So if the original and transformed Hamiltonians have the same functional dependence, then we say the transformation is symmetry. So that's the condition that S is a symmetry. And then indeed, we have the same form of physical laws, the same differential equation, if you want, that describe our system no matter where we are in which reference frame. Now, the insight that we want to give here is that reference frame are in general also physical systems. We usually describe them very abstractly by the choice of the coordinates, but in principle, when we want to perform some experiment in the lab, the coordinates are defined with respect to another physical system. And since they are physical systems, they should obey quantum mechanical laws and all other laws, of course. And so what I want to show with this cartoon here is that in general, when we are in a one reference frame, that's prime one, not only the system, which is this kind of wave packet, could be in the superposition, but entire reference frame with respect to which we can consider this system as well could be in a quantum mechanical system. And now, if this is so, we can actually ask two questions. Now, are the physical laws covariant under change of quantum reference frames, which seems to be a larger class of reference frame as compared to the classical ones? And second question is, in turn, can the assumption of the validity of the covariance under the change of quantum reference frame uncover new physics? And that's what I want to focus today on, the second question. So I would assume that our physical laws have a larger set of transformations under which they are invariant, these quantum transformations, and then I will try out of that to get some insight in the domain of physics that are not, at not least experimentally, not available. And so let me start again with the cartoon. Now, this is a situation which is easily but known how we should handle. We have a source of gravity. In the cartoon, this is Earth. And then we have a quantum mechanical system, a kind of an atom that moves or freely falls in the gravitational field of gravity. Now, we can describe this to a different level of approximation or exactness, even going into the quantum field theory in the curved space-time. And this recipe is hard, but it's available. Now, the situation in which we have a source of gravity put into superposition is a completely new situation in which the gravitational field and the metric, or if you want even the geometry, is not well defined. And so we might question how then we can describe the system in this situation. And there are different approaches to quantum gravity, which it's very hard to get even low energy limit that might be relevant even for the first experiments. So we might be even ignorant about the true theory about that. Definitely, there is no broadly accepted theory for that. And there is no even consensus whether gravitational field should be considered quantum mechanically or not. And now what I want to suggest with this talk is that we put aside the question about the nature of gravitational field and proclaim a principle of invariance under quantum reference frames to help us handle this situation. What does it really mean? It means that from the left-hand side figure, I can, by choosing an appropriate quantum reference frame, move to the right-hand side picture and then solve their dynamical problem and then go back. So what would be this in this cartoon? That would mean that there is a way, formal way, to sit on the Earth or to move into the quantum reference frame of the Earth. Now, from this quantum reference frame, the Earth is fixed, the gravitational field is fixed, the metric is fixed, and something else might be then in the superposition, for example, the probe particle, the atom. And now we can solve this dynamically. We know how it will fall into the gravitational field, this atom, in a superposition. And then only at the end, we move back to the initial reference frame and give the solution to the situation which we a priori didn't know how to deal with. So here's the outline of my talk. I want first to put some effort to describe quantum reference frames for a very simple transformation, namely translations. That will be enough to state the problem of interest. I will also introduce what we call generalized principal covariance. And then I would show you two applications, first for the motion of a test particle and then for the gravitational time dilation. And then I go to the generalization. And then I would abstract the notion of quantum reference frames transformation to the quantum conformal transformations, give a summary and outlook of the talk. So let's start with a known situation. That's classical reference frame. What you see here is three particles, if you want, three localized particles, classical particles, the blue, the orange, and the gray one. And then I would say that every statement about any of them can only be made relative to another physical system, much in the sense of a relational physics by Carlo Rovelli. And you see still that some of the particles have these flags, and the flag will indicate the origin of quantum reference frame, or reference frame here is a classical one, from which I will define the coordinates or the distances to other particles. And so, for example, if I choose the blue particle as an origin reference frame, then the orange will be that XA and the gray and XB. But then I can change the reference frame and move, so to say, jump to the orange particle, in which this is the origin 0. And then the other two will correspondingly have coordinates as through this transformation. So I will shift the coordinate of the gray one, and I basically reflect the coordinate of XA, of the A particle. Now, what we back in 2019 suggest is that very similar or identical transformation should be also applied whenever we have a well-defined localized particles. So there is nothing which prevents us in quantum mechanics to put the cats around these coordinates. And now the question is, what is the transformation that transforms the cats from the left to the right? And if in particular we take the whole basis for the A and B particle as a product of these bases and have this reference state, which is not dynamical in C, 0, then we may ask how we get another set of the cats that are given here on the right-hand side of the picture. And it can be shown that it can be obtained through a certain unitary transformation. And I will now introduce this unitary transformation. It consists of two parts. This is this lower equation. And let's us concentrate first on the gray part. So the gray part is something which where the B particle is shifted. So we just have a translation, a generator of translation for the B particle by momentum. And what is the parameter transformation is actually the position of the A particle in the previous reference frame. So it's just a shift operator for the B particle. But then there is a blue part of this transformation, which concerns the C and A. And we know that we actually interchange the roles of the quantum reference frames from C to A. So at the beginning, we have 0C XA, and then we have minus XA 0. So what the transformation that makes this change is something which we call parity swap. Namely, what it does, it first translate XA into minus XA, so it reflects the coordinate of the A particle, and then swap the role of the particle A and C. And that's what exactly it does. So it first makes from XA minus XA, and then swap these two states such that 0 will be assigned to A particle and minus XA to C. So altogether, the transformation is this orange transformation. So that's the state in the old reference frame, and that's the state in the new reference frame. And we get one from the other by applying this composition of two transformation, one being the controlled shift of particle B. I say control shift because how much we shift depends where XA is. This is not anymore a parameter. This is an operator here. And the second transformation after this controlled quantum translation is parity swap. And so when we have this, we can then, of course, apply on any such localized state, but also in any superposition of that, because it's a unitary operator, linear operator. And so we may ask ourselves, this is nice, but how it works on a real kind of wave packets if we have a delocalized quantum system. Now, the first step towards that is to check that the B particle is delocalized. So, but then nothing really interesting happened because we moved from one reference frame to another, quantum reference frames, but the B particle is somehow detached from that, and we can go through and really choose whatever arbitrary state for the B probe particle. What is more interesting is what if the old reference frame is in a superposition of two positions, and now we jump on it. Now what happens is that the remaining two particles, the old reference frame blue and the gray one, get entangled. And this is somehow easier to understand that there must be some correlations. Why? Because if I'm this light orange state, then I'm closer to blue, but further away from gray, then as compared to one in which I'm in this strong orange, where I'm further away from blue, but closer to gray. And that means that these two states, the gray and blue one, must be correlated. And indeed, if you start with a state as on the left-hand side, whereas superposition, A is in a superposition, when we move them, we will get something which is an entangled state like that. And it's entangled state because, first of all, A particle, the whole reference frame will be at two different positions, but also the B particle will be shifted depending where the A particle is. So if I apply this operator of B, I will get two different states for B, and therefore altogether it will be entangled state. And indeed, this can be obtained by applying our transformation. And so these quantum spatial translations can do something very interesting, namely, they can change the notion of superposition or entanglement. We conclude that these are notions relative to quantum reference frame. And in this example, it is very apparent because at the beginning on the left-hand side, we had no entanglement, all factorized states. The old reference frame is in a superposition, but when we jump into it, the remaining two systems, the new reference frame will be in a superposition, but when we jump into it, the old reference frame and the particle will be entangled. So superposition and entanglement are not absolute notions, but relative to quantum reference frames. And this is even nothing very dynamical. It's all kinematics, what I'm telling you now. Now, one can think about how can we then introduce the notion of the symmetries. I put it under inverted comma, quantum symmetries, given that we can change from quantum reference frames. We know what is the symmetry when we change from the classical reference frame, but now it seems that we have a larger set of transformation, and we should redefine our notion of symmetry. And the thing that we suggest back in 2019 in this paper by Giacomini et al. Was that is a very similar. We will define a transformation as to be a symmetry if the Hamiltonian now, not only about the probe particle, but also of the new reference frame, if the form of this Hamiltonian is preserved. So that is the old Hamiltonian on the left-hand side, and that's the transformed one. When we transform one, then A is not anymore a dynamical system, it's C and B. But what we assume that the functional difference of this new Hamiltonian, which depends on the B and C, is the same as the functional form of the Hamiltonian before the transformation of A and B. So although we have different systems before and after jumping to a new reference frame, we require that the differential equation of these two systems, first A and B and then C and B, is the same. And that will be then the symmetry. Okay, so that's basically all what I need for kind of, if you want, background knowledge of quantum reference frame. There is much more to be said about that. We have developed these quantum reference frames, not only we, but several other groups as well, to the full Galilei group, also to the Lorentz group. So it's one relativistic domain. And so people are still working on that. It's by no means a complete field or knowledge. But nevertheless, this simple example can help us to deal with the questions that I posed at the very beginning, namely, how does an object fall in a superposition of gravitational fields? So as just to remind you again, so we are interested in this left-hand side picture, but we don't know, we don't want to make any pre-assumptions about the nature of this gravitational field. Maybe even superposition will break down because of the because the quantum mechanics may break down at some scale. So we don't make any statements about that, but we make a statement that there is a way to change the quantum reference frame to a new quantum reference frame, that the dynamical laws are the same that govern the left and right hand side. But in the right-hand side, we know how to deal with this dynamic. This is the usual quantum mechanical systems on the curved space-time. We solve this problem and we go back. So what we want to now suggest is kind of a generalized principle of covariance, which would say that covariance and dynamical laws under quantum coordinate transformation, namely that physical laws retain their form under quantum coordinate transformation, not only under classical coordinate transformation, but also quantum. And what I mean with this is exactly the framework that I introduced in the previous slides. So let's see how it works.
Can I ask a quick question?
Sure. I retain the possibility to answer it at the end, but go ahead.
Okay. But it's just quick. What is the criteria for the difference frame in quantum systems? It is not evolved in time and not superposed. That is if and only if condition for the state is, we put the flag on that system.
So what is the criteria that something is a quantum reference frame? Is this the question?
Yes. How to judge we put the flag on that system? Okay,
I think that's a good question, and I would at the moment say, but we can discuss afterwards, any quantum mechanical system can serve for that. Okay, so for example, very often, even in the now when we talk, for example, we want to explain the decay of muons coming from the cosmic rays. Sometimes we say, oh, let's imagine we are in the rest frame of a muon, then we compute the decay rate, and then we move to our reference frame. In a very similar sense, we can do this here, only extending, for example, the idea that muons maybe move into superpositional relativistic velocities. And then we say, oh, let's go in our mind. We might not physically go in our mind to the rest frame of a muon, do calculation there, come back. Sometimes it could be a real physical system which we can attach the flag. But I would say, a priori, there is no restriction what is a reference frame. Reference frame is a physical system, and physical system should obey quantum mechanical law. I don't know whether I answered the question, but I would prefer to go forward, and then we may discuss afterwards.
Okay, thank you.
Welcome. Okay, so here is the example. What I want to show is this certain commutation diagram. So what you see here is initial situation. We have a source of gravity in a superposition. We have a probe particle, and we have the initial reference frame. Now, I have changed a little slightly the notation just to agree with the one in our paper. But what was previously C is now R. This is the old reference frame. What was previously A, the new reference frame, is now M. And what was the probe particle B is now S. Now, what I want to do is I want to apply the quantum reference frame transformation, to apply a unitary transformation such that I jump on the Earth, and then the particle and the old reference frame will get entangled, as we discussed this before. And then I will solve this problem here, namely falling of the system into the gravitational field of Earth. Here, I want to say that we draw only the probe system. The reference frame is not drawn, but one can draw also the reference frame. And then we move back into by inverse unitary transformation into initial reference frame, and we say how the free particle will move in the superposition of gravitational fields. So let's do it. So I start with the first picture, and I assume, although a specific state, but everything applies to the most general state, that the mass is in a superposition and the system is localized probe, and I have zero state for the reference frame. Then I move this superposition via reference frame transformation into entanglement between the system S and the reference frame R, just like we did this before. And now I'm starting from this second reference frame. This is just rewritten here, and dynamically solve the problem from 2 to 3. And now we can choose whatever the level of exactness we want to do it. Since this is a more of the conceptual paper now, I have chosen the most simple dynamics, which is given by, for example, work by Stodolsky from 1979, in which he says that I can describe the system in the gravitational field such that if I have a localized wave packets, then these localized wave packets in the semi-classical approximation will follow the geodesics. And so what I here discard is any dispersion of the wave packets. So I really treat them as a pointwise wave packets, but they are still in the superposition. So there is some quantumness here preserved. And secondly, there will be the relative phase, which will correspond to the difference of the accumulated proper time along these two geodesics. And that's the way how you can dynamically describe this superposition in a semi-classical approximation. And now I'm starting again from this state, and I want to go backwards with the inverse unitary transformation. So I can do that. And then I will see that what was the entanglement between the old reference frame and the system now transforms back in such a way that the system, the old reference frame, will factorize out. It's basically not relevant here. It was just a helping tool to make this transformation unitary. And what remains here is entanglement between the system and the position of the mass. With corresponding phases as given with this accumulated time dilation. And so at the end we have what we wanted to have and what was expected in a sense. If you think quantum mechanical, that this proparticle, the trajectory of those will be entangled with the position of the mass. Now one can ask oneself, how about the symmetry? Is this a problem where indeed the dynamics is invariant under this quantum reference frames transformation? And this is indeed true. If we think about in the weak field approximation, where we consider only the system and let's say the reference frame is very massive and doesn't contribute to that, is that you have a kinetic part of the probe system and potential. Now, when you move from this reference frame, which is obvious, to the one of R, what will you get under this S transformation, which is time independent, is again the free particle and the potential, which now depends on the relative distance between the mass and the system. So in this Hamiltonian is invariant even on these quantum spatial translations in which we can choose between different quantum mechanical systems. Okay, here is another application, and this is application of the time dilation. And I would be a little bit faster on that because it's basically a repetition of the previous example, but you go beyond pure Newtonian gravity. And you want to describe also gravitational time dilation. So what I have is, again, a commutation diagram. And so instead of the probe particle, I have a clock. And I have a clock that will store the time dilation. And in a superposition of two gravitational fields, then I will move into the reference frame of the Earth. The clock will get now in superposition and entangled with the old reference frame. This situation I can describe because the clock rate will depend on the distance to the mass. The closer to the mass, the slower the clock ticking is. And so I will basically get some entanglement between internal degrees of freedom, that's the clock rate, and the position of the clock. So I will have these two possible clock rates. And then I can go backwards and see this from the old reference frame and solve my problem. So here is again a little bit faster. I would say I will talk about now. The state is very similar with important difference that now instead of the probe particle having just a position, I have a clock. So the clock has a position, that's this, the C, but it also has internal degrees of freedom. For example, it could be some atomic clock, which I have to put in the superposition over ground excited state such that I have some dynamical evolution. And afterwards, so I have a more general situation. And so now I want to move to the new reference frame. I apply the S transformation and I get a new state. This state is very similar as the previous case because I have entanglement between the position of the clock and the old reference frame, but I also have these internal degrees of freedom that I assume at the beginning to be factorized out. Now, what happens now with these internal degrees of freedom as the experiments evolves? Well, we can use, for example, computation done in Zich et al. Paper back in 2011, where we consider a single clock in a superposition of two different heights in the gravitational field. And so what happens is that the two different amplitudes, depending whether the clock is closer or further away from the mass, the ticking rate will be different. So the time evolution of internal degrees of degree of freedom will be given by this expression, where we here have internal energy of the clock, and that's basically the energy of the ground plus energy of the excited state. And this parameter, the proper time, will then depend on how far the clock is from one or the other mass. The closer it is, the slower the ticking rate is. And so, at the end, we have a huge entangled state between the old reference frame, the position of the clock, and the internal degree of the clock. And of course, as before, we have these different phases as given also in the previous case. Now, the last step is just going backwards. And by inverse reference frame transformation, we get into the initial reference frame. And in this initial reference frame, the old reference frame will be factorized out. The position will be localized of the clock because we kept this localized, for example, in the trap. But what gets entangled is the position of the mass and the ticking rate of the clock with corresponding phases. And that's exactly what we here see. Depending whether we are closer or further away of the mass, we will have a blue or orange ticking rate. Okay, so let me conclude this example with some numbers. They are very, very discouraging, of course, for these effects, but we also don't expect that anything which has to do with some superposition of geometries is easy to observe. But let me think about some Gedanken experiment and having, for example, masses of 10 to minus 8 kilogram, having distances of a 10 to minus 5 order or meters of their magnitude. Well, then for the duration of the experiment of 1 second, the time difference in the accumulated proper time difference will be 10 to minus 32 seconds, which is a very small number. However, what I want to say is that this is a very tiny effect, but still many orders of magnitude closer than what usually people say that the quantum gravity effects appear, and which are high energy quantum gravity effects of 10 to minus 44 seconds. These are low energy effects. And secondly, what I want to say is that this, I would say, would be a proof of a genuine superposition of spacetimes. And the reason is that if you have a localized clock in your laboratory, and this and the ticking rate gets superposed, you get some uncertainty in the ticking rate. The only reason why you can get that is that your space-time is not well defined. Otherwise, you can get this even if the space-time is well defined, if the position of the clock is not well defined. But if you ensure that localization of the clock is precise, that could be only due to some fluctuations in the space-time. And if this effect doesn't depend on the nature of your clock, it's a universal effect, and it is an effect of the time itself and not of the clock. Now, what I want to do next is to show you how this principle of general covariance can help us distinguish different alternative approaches to quantum gravity. So what you see here is a picture which will be true for any theory that obeys our general covariance principle. And what you see in the lower picture is the source of the mass, and you have a pro-particle in a superposition of two positions. Now, what will happen is this pro-particle will start to fall down towards the mass in the superposition. And the same picture, the same effect, so to say, can be seen from the point of view of a pro-particle. If I sit on a pro-particle, it will be the large mass that is in a superposition. But nevertheless, even then, this large mass will be, so to say, fall towards the down towards the pro-particle, such that the relative distance decreases. What you see in the right-hand side is these two views from the view of the semi-classical gravity. A semi-classical gravity is a gravity in which the source of the gravity is sourced by the average gravitational field. So what you have here below is the source of the gravity is at the center. So the average and the real one is the same, and no doubts that then the pro-particle in superposition will fall towards the mass. However, if we move into another reference frame of the pro-particle that is exactly in the middle of these two possible positions of the large mass, the average gravitational field will be zero, and therefore the pro-particle will not be attracted by these masses, and everything will be staying still as it is. So we see that semi-classical gravity does not obey the general covariance, because the phenomena from one or the other reference frame will be physically different. In one case, they will approach each other. In another one, will stay still. And the similar is also for the collapse model. The lower picture is the same, because you have a small mass in the superposition when the collapse does not activate. But once you get into this reference frame of the small particle, the large mass will be in the superposition. The collapse model says, no, they cannot survive superposition. They start to decay, to collapse in one or other position, 50-50. And therefore, you will have some kind of incoherent situation above and coherent below, saying that collapse models also do not obey general covariance. So that's a way also to test certain alternative quantum gravity models. Now we can go to the generalization. So I want to a little bit speed up. We can think about what if we have not one mass, but many masses, and I have an arbitrary distribution of mass on the left and right-hand side. Now, the situation one we can ask, can we always find a reference frame in which the metric becomes definite? Because this was the idea. It has an indefinite metric, choose a quantum reference frame to make it definite, solve the problem, go back. But now the answer is, if we have a really arbitrary mass configuration, this is not possible. And the reason is that we are restricted to superposition of relative coordinate distance preserving transformation, which are global translations and global rotations, because only then, and that's the situation, we can put one configuration on the top of each other and therefore make them really the same, very same space-time. And so that's, if it is an arbitrary configuration, will not be possible. However, one should not think that this limits us to a very trivial, or if you want, diffeomorphism related situation, because the presence of the pro-particles breaks the symmetry. So the pro-particle could be either closer to Jupiter here or closer to the Mars here, and then the events, which will include also the position of the particle, are not diffeomorphic related in totality. Only the space-times without the pro-particles were related by the global translations and rotations. And now this generalization to many masses that are related through translations and rotations can be done. And if you're interested, you can check this in this paper. It's more complicated, but still very straightforward. Now I want to go a little bit beyond that for the rest of my talk and talk about conformal transformations. Now, imagine that you have transformations between two conformally related spacetimes. Again, I start with a cartoon and then I will be more technical. So we have something where as an expanding universe. Now we want to connect not only those situations, but also the situations which I can think about quantum conformal transformations, namely that you have a spacetimes that are in the superposition of different conformal factors. Which is a quite unusual and very speculative situation, but nevertheless, is something that one can think of if one allows for quantum superpositions. And so what I will more specifically like to look at is a Klein-Gordon field in a superpositional spacetimes. And what you see on the left-hand side is a set of conformally related metrics. And on this matrix live a quantum field. And imagine that you have a state of a quantum field, which is in a superposition of these conformal related metrics. And again, I want to find a way to jump to a specific quantum reference frame in which I might have a definite metric, but maybe something else will pick up the superpositions. And I will have, again, analogous or equivalent situation. So I want to map the field in a superpositional spacetimes onto the field in the Minkowskian spacetime with superposition of masses. And so I will, why this is interesting? But first, it's interesting because we go beyond quantum coordinate transformations or beyond diffeomorphisms, because the conformally related metrics are not diffeomorphic related. So we see that we go beyond mere coordinate transformation. We abstract the quantum reference frame transformation to go beyond pure coordinate transformation. And secondly, so far I have always particles, and here for the first time I have quantum fields as probes, and this might be interesting as a step to more fundamental notion of quantum reference frames. And so let's tell you what we have done in this last paper. So what we have here is we consider all spacetimes that are conformally related by a conformal factor omega. And what we, on the left-hand side, we have a Klein-Gordon field on the curved spacetime. And it turns out that this Klein-Gordon field on the curved spacetime is not invariant under conformal transformation. However, if you're allowed to have a spacetime dependent masses on the right-hand side, then you will see that this Klein-Gordon field with a spacetime dependent mass is invariant under conformal transformations. So this allows us to think about a triplets of the variables: metric, defined by the conformal factor, quantum field, and mass. And if we have a triplet of these variables that satisfy a Klein-Gordon equation, then we can transform in this form to another triplet that would also satisfy the Klein-Gordon equation with time, a space-time dependent mass. And furthermore, this transformation builds a group. So we can have a whole family of the solutions that are related to via the group transformations that's all satisfy Klein-Gordon field in the curved spacetimes. So that's the technical part that we need. But this technical part allows us, after we quantize the Klein-Gordon field, which can be done, and I have no time to go to that, to define a very specific quantum reference frame transformation, namely the one in which now I have this triplet of variables, but I put their cats because now I can define them as quantum mechanical systems, states, where I have a metric, I have a field, I have a mass, and then apply then this transformation as introduced below to a new state of the metric, new state of the field, and new state of the mass of the field. Where here, what I really take are eigenstates of the field operators. This will be my basis in which I will decompose all my states of the field. And furthermore, I want to say that the state of the metric is nothing here very mystical, because everything is defined by the metric, by the conformal factor. So it's just a Hilbert space built on the conformal factors that represent these metrics. And so having this transformation, now I can play around with my initial game. Namely, I can think about situation in which I have superposition of different metrics with the fields, all with the same mass. And by this transformation, quantum reference frame transformation, I can transform this superposition into another part, namely such that I can think about a single metric and then all possible superpositions of these fields in different space-time dependent masses of the Klein-Gordon field. Okay, I'm coming to the end of my talk. That's exactly 2 minutes left. And I want to tell you what I think is valuable to do next in all this field. I think it will be good to extend and apply frameworks to quantum field quantum reference frames. So here we still have the pro particle in the last contribution being a quantum field, but the quantum reference frames were the mass or this conformal factor, and it will be nice to extend to arbitrary quantum fields being quantum reference frames. The next thing, all our computation are still within this semi-classical approximation for the massive objects and gravitational fields. What I mean with this is that the metric or the gravitational field that we consider are superposition over classical fields. They are in the, for example, Newtonian example that we had at the beginning, with the only source of the gravitation was the masses that we were at a certain positions. But if we go beyond the Newtonian approximation and we think about contribution to the gravitational field due to momenta of the metric or the full stress energy tensor, that would mean that we have to talk or not only about the position, but also the momenta of the source of the gravity. And then necessarily we would have some restriction coming from the quantum mechanical states of these sources of gravity, which are not just semi-classical because there is uncertainty in position momentum. So that is something which is very non-trivial going on, and I can expand on that in the question time. And finally, it would be interesting to design experimental proposal for testing the generalized covariance principle and extended symmetries. So what would even mean experimentally to jump in another reference frame? And I think the question during the talk was also related to this. And here's my summary of the talk. I wanted in the first part of my talk to suggest a general covariance principle while basically staying agnostic about the nature of gravitational field sourced by a mass in superposition. And this helps us to describe the moving over test particle in a superposition of geodesics or the clock sticking rates in the superpositions. But once one accepts this general covariance principle, one can then have an independent argument in the favor of some quantum nature of gravitational field, because we said that, for example, the collapse models or the semi-classical gravity would not be obey that. So although we cannot pinpoint which exactly quantum theory gravity is the one that we eventually should accept, we can say that it has to obey this general covariance principle, and that means that it has some kind of a quantum nature in itself. We can assign the cats to that, and we will get the validity of general covariance principle. And finally, in the last part, I tried to extend the notion of quantum reference frames beyond the quantum coordinate transformation, and in that way somehow abstract the notion of the quantum reference frame transformations. And with this, I would like to thank for your attention.
Thank you very much for the great talk. Is there any question?
Thank you very much. Very interesting talk. Yeah, I'm very enjoyed. And I have a question. So I'd like to understand more deeply the quantum reference frame formulation. So can you apply your theory to a double slit experiment? So, okay, so let's consider a particle which pass through a double slit and go to the screen. Then we have an interference pattern on the screen, right? But from the viewpoint atom or particle, then the screen is a superposition which are located in different position, right?
Exactly.
Then, so I'd like to understand why on the screen we have again the interference pattern. So for the particle, so we have just two different screen. The screen is just superposed in a different position. So particle just go straight to the screen itself. So I cannot imagine why such an interference pattern happens in such a viewpoint. Could you explain that?
I think I understand what you're asking. It's indeed true. So if you have a particle in a superposition, then these quantum reference frames would suggest that from the particle point of view, the entire universe is in a superposition, if you want. And in particular, the double slit screen or whatever the experiment is. And now you ask me, I don't, how should I understand the interference of that? And I think the answer is, it's not different than the situation in the old reference frame. In the old reference frame, it was the particle in the superposition, and whenever we have a particle in superposition, we have interference. And now the object that I'm considering now is not a particle, but it also has a wave function, which is in a superposition. Maybe this is a whole double slit experiment, a double slit screen, sorry. And this object is now in the superposition and obey quantum mechanical laws. So it has to have interference. I know that this is a very trivial answer, but I would not know a better one.
Thank you very much. Thank you.
I hardly can hear now.
Thank you.
Yeah, welcome.
Hi, Časlav. I have a question on the middle part of your talk where you, can you hear me actually? Or?
Yes, I can hear you, yeah.
On the middle part of the talk where we were discussing how to go from, the quantum reference frame in which the Earth is in superposition to basically the frame of the Earth where the old frame is in superposition. Can you say a little bit more about the background assumptions here? So you're using the geodesic equation, it seems. So are you really assuming here full-fledged general relativity and in principle arbitrary coordinate systems in which this transformation is supposed to be understood? Or are you assuming some special class of coordinate systems which you use in which you're basically writing the localization of your systems?
So let me go back. So that's basically the
somewhere on I mean here, so when you write these X and so on, I mean, so is that can that be an arbitrary coordinate system, or are you assuming some special class of coordinate system? So the reason I'm asking is that here the transformation gives you something like a linear transformation like XS minus XM.
Yes.
But
yes.
if I was to do, if I did a, like a non-linear coordinate transformation, then that wouldn't be linear.
Yeah. So no, here we use only the translations group, and there are only linear transformations. The question is, of course, and that's something that is interesting, and I think people think about that, how to extend this to arbitrary diffeomorphic changes, so that arbitrary quantum coordinate transformation, we are not that far. So these are what was just linear transformations. Actually, transformations that preserve, okay, so more precisely, it's the transformations that preserve the, as I said, preserve the relative distances. So like translation rotations, because this is important, that the relative distance between M and S is preserved.
Mm-hmm. Okay, yeah, I mean, I understood that, but then basically but is there, I mean, somehow physically distinguished way of determining that coordinate system, because in other coordinate systems, the transformation won't look the same. So somehow, I guess you're assuming a certain physical significance associated with these XMs or so, with the localizations, no? So I mean, so what I'm trying to say is, like this quantum reference frame transformation, because it's, I guess, translations and rotations, that form won't be true in all coordinate systems.
It won't be true in all coordinate systems. I agree. So the more work has to be done to extend the whole thing into the arbitrary coordinate transformations.
All right, thanks.
And I think then we will be able to deal with a more complicated situation than this situation in which we have masses configurations that could be put on the top of each other.
Okay, thanks.
Any other question?
This is just a clarification question about your definition of a quantum reference frame. Is my understanding correct? Does it consist of a Hilbert space together with a pure state and a Hamiltonian, and the pure state is left invariant under the Hamiltonian? Like what's the actual, I guess my question is, what is the definition of a quantum reference frame?
So
like for qubits, let's say, what is a reference frame for a qubit?
Yeah, another qubit. But the qubit is maybe not the best example because these are finite reference frames. So here is basically what we're doing always infinite dimensional Hilbert space. There are enough resources. So I would say that the quantum, the description with respect to a quantum reference frame is description which is any description that we have also like in our lab. This is you have all system external to the reference frame, you assign a pure state to them, you assign a Hamiltonian. That's the viewpoint of the quantum reference of any reference frame. Now you can do the same by assuming that by changing the system from which you observe external ones. So to say, you can have many quantum reference frames, of which you pick up one of them, or many quantum mechanical systems, which you pick up one to be a quantum reference frame. With respect to this, you define the Hilbert space of the all external to it, and the Hamiltonian of all external to it. Then you can pick another subsystem of this set of quantum mechanical system, and you define then the pure state with respect to this another one, external to this another one, and a Hamiltonian. And then you can ask yourself what it means to choose from one to another. I don't know whether it was clarifying.
I may ask you later. Thank you.
Any other question from online?
Can I ask one question? Can you hear me?
Yes, yes.
Yes, yes.
Oh, great. So thank you very much for the very exciting talk. My question is, if we can use quantum computers to experimentally test your kind of proposals. So for example, in the slide where you showed some numbers, the resulting time difference was very small, like 10 to the minus 32, I think, right? But
Yes.
that is because two planets were not so different. I mean, not so apart. Like I think your assumption is 10 to the minus 5 or something. And also
Yes.
these two planets were very not so heavy, right?
Yes.
But in future, we expect, well, not I actually, but we expect to have a big quantum computer. Then we can entangle two quantum computers at distant places, I guess. And then by
Yes.
doing this, maybe you can increase the distance between these two massive objects. And then,
But-
maybe, the time difference might be detectable. So I'm just, wondering.
No, but what I expect in the quantum computer when they get entangled there, what could be entangled are some internal degrees of freedom of the computer. So you will do with the qubits, you will have some maybe atoms that could be an excited and the ground state. That will be the qubit. And so you can have two atoms that are entangled with internal degrees of freedom, but nevertheless, the masses are more or less localized where they are. So that will not induce these kind of effects. You really need a massive object to be in superposition, not some internal system in the superposition.
So you mean, but it's possible to, make the difference between two atoms very far away, right?
So you say like if we have to trade off instead of having very large mass on a small distance to have small
to have a very large distance.
Yeah.
Then is it possible on the Earth? I mean, can we have a
I didn't look at the numbers, but I doubt that it will be enough. I doubt that will be enough to overcome the problems of the lacking mass, even if you have a very large distances with the small masses. Yeah.
Okay, I see. Yeah, thank you very much.
Welcome.
One more quick question. If not, let's thank the speaker again.
Thank you.